We're going to talk about CSF production at the choroid plexus. I wanted to talk about the cellular aspects of how this is done. So what we're looking at is a depiction of the choroid epithelium. Note the orientation of the epithelium. We have the basolateral membrane that is facing away from the CSF. So this is facing towards what we'll call the choroid interstitial fluid, or ISF. And then you have the apical membrane with the brush border facing towards the CSF side. The choroid plexus is enriched with capillaries that are relatively permeable, and these capillaries are providing the water and the electrolytes and other solutes that are going to ultimately comprise the cerebrospinal fluid. And so the production of the CSF involves moving those solutes selectively from the choroid ISF, which is outside of the brain fluids, brain fluid compartments, into the CSF. So remember, these epithelial cells that comprise the choroid epithelium, they're linked together by tight junctions. Although these tight junctions are relatively leaky compared to the blood-brain barrier tight junctions, it still does prevent free movement of solute and water between the choroid and the CSF. So the way water is moved is by creating a concentration gradient that's going to in the CSF that's going to draw the water from the choroid ISF into the CSF. So the first step in how this is accomplished is by creating a favorable electrochemical gradient for sodium movement from the choroid ISF into the epithelial cells by the sodium-potassium pump. So sodium-potassium pumps are located on the apical membrane within the brush border, and this is going to facilitate vectoral movement of sodium and ultimately other solutes that are going to be following sodium into the CSF side. Also, similar to the role of the sodium-potassium pump and other cell types, the sodium-potassium pump is extruding sodium, in this case out towards the CSF, and is bringing in potassium, causing a high potassium concentration inside the cell. What's not shown here are potassium channels that are allowing the potassium to flow right down its electrochemical gradient, which is going to ultimately promote an inside negative membrane potential inside the epithelial cell, just like what happens in other cell types that we've discussed. Because of the activity of the sodium-potassium pump, there will exist a very favorable electrochemical gradient for sodium to move from the choroid ISF into the epithelial cell. That is, the sodium concentration inside the epithelial cell is very low compared to the concentration outside in the ISF. So this is going to create a concentration gradient which is going to favor the inward movement of sodium. Also, because of the role of potassium permeability in generating a resting membrane potential, because the resting membrane potential is very negative, this is going to make a very favorable electrical gradient for sodium to move. So based on those two gradients, sodium has a very strong driving force, or want, so to speak, to move from the ISF into the epithelial cell. And it is this driving force that's ultimately going to play a big role in how sodium is allowed to be moved into the CSF, thereby drawing water in the process, creating the cerebrospinal fluid. It should be noted that an important aspect of the CSF production is making sure that the pH of the CSF is going to be appropriate based on the acid-base condition of the brain. So remember, on a moment-to-moment basis, the pH of the brain fluids is determined by the partial pressure of carbon dioxide. Long-term regulation of brain pH involves selective movement of bicarbonate into the CSF. If it is for some reason desired to increase the brain pH, that is, decrease the free proton concentration, then we will want to move more bicarbonate into the CSF. Conversely, if it is more desirable to decrease the brain pH, that is, increase the free proton concentration, then we will want to bring over less bicarbonate, in that circumstance. So let's see how this all works. Again, keeping in mind that we have a favorable electrochemical gradient for the movement of sodium from the choroid ISF into the epithelial cell, the first step in the formation of CSF is driven by sodium movement, is the movement of sodium from the choroid ISF into the epithelial cell via a secondary active transporter called the sodium-proton antiporter. So sodium is able to move down its electrochemical gradient into the epithelial cell. In the process, promotes the extrusion of a proton out into the choroid ISF. Once the proton is moved out into the choroid ISF, it is able to react with free bicarbonate, forming carbon dioxide. The carbon dioxide, as a freely diffusible gas, can diffuse across or through the membrane of the epithelial cell, the basolateral membrane, and into the epithelial cell. Carbon dioxide then can react with water to form a carbonic acid, which will dissociate into a proton and a free bicarbonate. The proton that is produced in this reaction can then act as a substrate for the sodium-proton antiporter and effectively continue to cycle around and around out of the cell into the ISF, and then from the ISF back into the cell, and so on and so forth, each time promoting the movement of sodium from the ISF into the epithelial cell. The bicarbonate, on the other hand, can move either back towards the choroid ISF or move out towards the ventricle to be part of the CSF. The amount of bicarbonate that will move back out the basolateral membrane towards the ISF, or how much will be joining the CSF, is dependent upon the pH demands of the brain. So this cycling of protons and potentially bicarbonate, each time this occurs, brings more and more sodium into the cell. So ultimately, though, the sodium is moved out the apical membrane via the sodium-potassium pump out into the ventricle. This net movement of sodium from the choroid ISF into the CSF, is going to create an osmotic gradient that will draw water from the choroid ISF out into the ventricle.